Hi, welcome to an introduction to quantitative comparison questions on the GRE. This is Emily Sledge with you today. And just in case I slip into it later, you'll often hear people call these questions QC. I'll probably do that a few times today. This is what QC questions look like. There's always a quantity A and a quantity B. And you always have 4 answer choices. That's one of the great things about this kind of question. Usually on standardized tests, there's 5 choices. If you were ever stuck making a totally random guess, this increases your guessing odds, of course. And the other piece of good news is that it's rarely necessary to do a completely random guess. It's typical to be able to eliminate 2 choices with certainty, even on the hardest questions. And we'll see how today. So in addition to the quantities and the choices, which are always the same and always in the same order, you can have a piece of information given to you. You're expected to use this constraint as you think about which quantity is greater. So first order of business, if you have not already done this, is memorize the choices. Luckily, they're pretty straightforward. A corresponds to quantity A being greater, which is convenient. B to quantity B being greater. C is when they're equal, and D is when you can't tell. So in class today, on most of the slides, we'll have a little key to help you out, but in future lessons, you'll be expected to know this. And I think by the end of even this segment, you will. About those answer choices, although they don't use the word always in the text of them, you should read them as if always is there. So you'd pick quantity A only if quantity A is always greater, no matter what. Likewise for quantity B being greater, and you'd only say that the 2 quantities are equal if they're always equal, regardless of the values of the variables, for example. The only choice that doesn't have always in it, sort of the default when always fails, is choice D, that you can't tell what the relationship is. And since that's the unique choice, you should actively try to prove D. It's easier to disprove that something is always true than to prove that there's a pattern at work. So for example, you can prove that quantity A is not always greater if you can show that there's at least one situation in which quantity B is greater. And that'll be our goal for a lot of these problems. And so let's return to that first example with that in mind. To try to prove D, pick a number, plug it in. It may look like, x is equal to 2 of y. X is double of y. So your first inclination might be that x is a larger number. And in fact, that is true when you plug in positives. And so with one single case, we've narrowed this down in terms of answer choices. If we show that at least quantity A could be greater in this one particular case, the answer could be A. We would just have to prove that that's always true. The answer could still be D if it's not always true. But we know for sure that B is not possible, because here's a case where B is not greater. And we know for sure that it's not always true that the 2 quantities are equal, because we've shown here A is greater. So C is eliminated. And this is what I mean by it's almost always possible to eliminate 2 choices with one simple check. Our next thing to do when trying to prove D is just see whether we can find a case where quantity B is greater. And it turns out when you plug in negative values, doubling y means x becomes even more negative. So A is less in that case, and B is greater. So once you have those 2 cases, you've proven D, and D is the answer here. Let's take a look at another one. Here, no constraint given, no information about x at all. So we're free to pick any number we want for x. Let's do that with proving D in mind. So positives are a great place to start. You square a positive integer, and you get something bigger. And so in this case, our remaining choices are B and D. Now we pick another kind of number with the goal of trying to make A bigger. Might come in handy if you remember properties of even exponents. Even exponents hide the sign. And so like if x were -2, when you square it, you get a positive value. So any negative, when you square it, you get something bigger because you get something positive. Okay, that doesn't help us though, because this shows that b is greater again. Okay, so our answers are still possibly b and d. We haven't proven b, notice, with two cases. It's easier to try to prove d by finding an exception. So fractions provide the exception. That's another case where when you take them to a higher power, a fraction times a fraction gets smaller. And in that case, a is greater. And we have proven d at that point. All right, here's a final example of the idea of testing values. A little bit more complicated, but again, no information given about x, so we can plug anything we want. Okay, 2 seems simple until you kind of do it. It's not the worst calculation ever, but certainly not the easiest that we could have plugged in. And this will happen to you on the test. If you pick an initial number that just turns out to be too annoying to test, pick something else. All right, 0 is a little easier to plug because some of those terms drop out and you end up with 0 plus 3, 0 plus 0 plus 9, easier to calculate. And we've come up with a quantity b is greater case. Plug in other numbers, see if we can come up with a different scenario. And luckily 1 works out to have a being greater. And we've proven d at that point. All right, so we picked an initial number that didn't quite work out. We regrouped, picked 2 other numbers, achieved the goal of proving d. And I don't want to make it sound like you have to start dropping numbers into the quantities every single time. There are alternatives. And unfortunately, the alternative is algebra. A lot of people are like, oh no, I was hoping to dodge that. But algebra is a good way to go on QC questions, because a lot of times you'll get kind of an algebraic expression in your quantities. And the cardinal rule of algebra is that when dealing with an equation, you have to do the same thing to both sides of the equation. So if you add 2 to the left side of an equation, you have to add 2 to the right side of the equation to make it balance, to make it still equate. Same is true if you're dealing with inequalities, right? You could add 2 to both sides of an inequality, you don't change their relative values, and so that's a valid move. Why do we worry about that here? Because quantitative comparison questions are basically like an implied inequality or equation. Our job is to decide, is quantity A greater than quantity B? Is the greater sign going to go here? Are they equal? Is an equal sign going to go here? Or is quantity B greater than quantity A? So should there be a less than sign here? So you can simplify as if there's a sign here. We're just working towards figuring out what that sign is. So on this one, you may notice that x squared is present in both quantities. Go ahead and subtract it out. And think back to when we plugged in numbers. Whatever number we plugged in for 0 there, x squared is going to be the same in both quantities. So if we remove that identical amount, we haven't changed their relative values. From here, you can simplify by grouping things. So by subtracting 3 from both sides, you get rid of constants in quantity A and you kind of group them all in quantity B. Next step would be to group the x's. Add 6x to both sides and you group all the x's into quantity A. You cancel them out of quantity B. And you're still at a point where you may want to plug in some numbers, but notice that it's greatly simplified. It becomes a lot easier to see what numbers you would want to plug in and easier to do the actual plugging. So just for example, if x were 1, A would clearly be greater. 10 is greater than 6. And when you plug in 0, 6 is greater than 0. And we've proven D. Okay, so you can either clean it up first or you can start plugging from the outset. So as you plug, you may have noticed that we've tried a variety of types of numbers. Here are some typical value ranges where you're gonna get types of numbers that tell you something. So you can have negative numbers, positive numbers, and moreover, you want to occasionally plug in fractions versus integers. I like the idea too of plugging in really, really large numbers, large round numbers like 100, positive 100, negative 100, good ones to plug. The idea is that after you try your first number, which is, typically going to be your usual suspects, 0, 1, something easy to plug, you try something weird, something different. Now, there are some QC problems where it looks like you've got a variable, and up to now, we've just been throwing numbers in. But here we've got a picture to work from. And these variables actually were not free to pick. Let's take a look at why. There's two rules in geometry that have to do with the number 180. And one of them is that angles that form a line, such as y and 60 here, notice that if you added them up, they form this horizontal line. Those add up to 180. So y really isn't free to be anything it wants to be. It has to be 120, so that it'll sum with 60 to be 180. There's another rule about 180, and that is in a triangle, the three angles add up to 180. So when we look at x has to add up with this unlabeled angle to be 180, but 50 and 60 also have to add up with that same unlabeled angle to be 180. And what that means is that x is the sum of 50 and 60. So notice that you could figure out that this unlabeled angle is 70 and just back 70 out of 180, or you can get there directly by adding 50 and 60. Either way, x and y have actual values. Your job here is to figure out what they are and just compare them. And here the answer is B. All right, so non-variable variables. You just have to dig a little bit to get the value. Here's a case where there are no variables at all. When you're faced with numbers like this, especially large numbers, you certainly can't plug these into the calculator and actually figure out what they are. You're going to have to put them in a form that makes them easier to compare, some common form that makes comparison a little easier. So right now we've got 240 as bases over here. We've got 8,000 as a base over here. That's not common. We've got different exponents, 5 and 10 and 15. But you may notice some similarities. 200 times 40 equals 8,000. So maybe something can be done with that. 5 and 10 add up to 15. And you may remember with exponents, if these had the same base, you could add the exponent and get an exponent of 15. They don't have the same base, so we'll have to do something slightly different. And what you could do is realize that you could split this up. Here you have the common base of 8,000. So working backwards, if you multiplied these together, you add the exponents. 5 and 10 make the 15 that we started out with. So what's the idea behind doing this? Now we've made the exponents the same, we can compare the bases. So compare 200 to the 5th to the 8,000 to the 5th. 40 to the 10th to 8,000 to the 10th. So the exponents are the same. You can almost ignore them. Of course, a larger base is going to lead to a larger resulting number. And this is literally a case of bigger times bigger on the quantity B side versus smaller times smaller on the quantity A side. Pretty easy to see that you get a bigger result in B. Now there's other ways to go. We could have exploited the fact that 200 times 40 equals 8,000. We could have found common ground in common bases and manipulated quantity B that way. Might be something to do on your own paper if you want to pause the recording and try that out. But for now, we'll proceed. Here's another theme, and the idea of testing strategically. If the GRE gives you a QC problem where one of the quantities is just a plain number, it will always be quantity B. So if there's one really simple quantity, it's always B, and quantity A would be the more complicated one. And this one's a doozy. I certainly wouldn't want to solve this. It's an inequality for one thing. It's also got exponents in it with variables as the exponents and different bases. This would be a nightmare if you actually had to solve for n. You're helped a little bit by the fact that n is an integer, but it helps to think about what integers you'd want to plug. Quantity b provides that clue. We don't know exactly what n is, but we don't care. We care about its relationship to the number 6. So use quantity b, cheat off of that easy quantity. That's the first number you should plug for n. And in fact, I would not feel comfortable plugging only 6 personally. I think it's a good idea to plug in the number above and below it, certainly here where there's an inequality going on. So here are our powers of 2 with 5, 6, and 7 plugged in. Okay, powers of 2, you should recognize those. And powers of 5 with 5, 6, and 7 plugged in for n. And quantity A talks about the largest value of n for which the inequality goes this way. The power of 2 is greater than the power of 5. And that really only happens when we plugged in 5. Once we plug in 6, 7, etc., the direction goes the wrong way. The power of 5 is bigger than the power of 2. So it makes it a little easier with these numbers in front of us to go back to the language here and figure out what they're asking. The largest value of n for which this works. Well, this was the last one for which it worked, when n was 5. And so that means that quantity A is 5. Okay, and we got there more quickly than we would have if we had started plugging in 0, 1, 2 for n. Start at 6. They've given you a huge hint with quantity B. You have a calculator on the GRE. Blessing and a curse, because sometimes there's an easier way and the calculator is just there distracting you into doing math that you don't necessarily need to do. I'm going to give you a minute to think about this question. Try doing it with a calculator. Think about a common sense way to go. All right, write down an answer on your paper if you've had time to think about it. We have 2 different exam scores possible. Or coincidentally, all these people have gotten exactly the same score. Seems a little suspicious to me, but there you go. We have 90 and 94 as the only scores people got. And what you might also notice is that the juniors, the people who got 90, there's more of them than there are seniors. So that complicates things. With averages and figuring out the average score, things would be a lot more straightforward if there were the same number of people getting each score, because then you could just do a simple average. But that also provides the little shortcut here. If we actually calculated the average, you'd get it by finding the total of all the scores divided by the number of people or the number of scores. Same thing here. And so to find the total of all the scores, you take the 120 juniors times their score of 90, that's their total points, and then the 100 seniors times their 94. And of course you have 220 people total. And notice this is a multi-step calculation. This would definitely be one that you'd want to do on the calculator while also kind of tracking the steps on paper, much as we've done on the screen here. And the number that you get is 91.81 repeating. So clearly quantity B is greater. But you can arrive at that same result in a more common sense way. Do the wishful thinking. What if there were the same number of juniors and seniors? Well, then the average score would be smack in the middle, right? Because both sets of students affect the average equally. So the juniors pull us down to 90, the seniors pull us up to 94, and they balance out in the middle. That middle benchmark is big with weighted average questions. And with this kind of thinking, we can look at what it means when there's more juniors. If there's more people scoring 90, they pull the average down, and there are fewer people scoring 94 pulling the average up. That means the actual average is going to be somewhere in this range. And on QC, it doesn't really matter where in this range. What we see is that it would have to be less than 92. And that's good enough for us to conclude that quantity B is greater. Okay, so you can get there with a little bit of a shortcut if you think in a common sense way. Don't overlook that. All right, going to give you a set to practice on your own. This one I'll put a timer up on the screen. Good luck. Well, welcome back. Before we go over these, make sure you have 3 letters written on your scrap paper. Commit yourself to 3 answers, even if you're not quite sure about any one of these. And I guess I lied when I said earlier we'd give you a key to the to the answer choices. Just as a quick reminder, A is that quantity A is always greater. B is that quantity B always is greater. C is that they're equal. D is that you cannot tell from the information given. All right, so we'll go in order here, top to bottom. X is negative in the first one. And we've got x to some power in both quantities. And what's relevant about these powers is that they're both odd. Odd exponents don't hide the sign of the base, whereas even exponents do, right? X squared, if x is negative, x squared will still be positive. But not so with the odd exponents. We know both quantities are negative, but the question is, how negative are they? Easiest way to find out, plug some numbers. So with integers, you'll quickly find out that a negative integer to the third is going to be less negative than a negative integer to the fifth. Here we have -8 and -32 as our examples. So notice that 8 is less negative. That makes it greater. -32 is more negative. That makes it smaller, actually. With decimals, here's where it's good to remember that decimals or fractions, when you take them to higher powers, they get smaller and smaller and smaller. So when you're dealing with negatives, it's getting more and more, less and less negative, closer and closer to 0 the higher your power goes. So it turns out higher powers of a negative decimal are bigger. And here's our proof of D. Sometimes A is bigger, sometimes B is bigger. If you're not quite as well versed in decimals, I would certainly do this one in the calculator as opposed to on paper. Easy enough to do so. You could also use -1/2 and reach the same conclusion. Here's our second problem. Pretty straightforward. Some similarity in the phrasing of the quantities. 2's in A instead of 3's in B. Let's plug. 0, easy one to plug. 100 just because it's big and round number. And it turns out that's enough to show that sometimes A is bigger. -2 is less negative than the smaller -3. And with big numbers, it's obvious to see which is bigger. We've proven D. But this one is also a candidate for that more algebraic approach, right? There's so many similarities in the quantities. Why not just group everything in one of the quantities? So subtract 2x, add 2, you cancel everything in A, and you group everything, every variable, every coefficient into quantity B. Little easier to see, why we're getting the results we did with the numbers that we plugged. If x is greater than 1, B is positive and therefore greater, and vice versa. So again, the answer is D, either way. Third problem in that set has absolute value bars. So remember what these do. If they turn whatever's inside positive. Okay, so if this had been a +7 inside the absolute value bars, they'd basically do nothing because 7 would already be positive. But with a -7 in there, it just turns it into +7. And so we've got +7 on the left, -n still on the right. Multiply both sides of that by -1, effectively moving the negative sign over. And n is -7. So this is one of those problems where a variable isn't really a variable. You just have to do a little work to figure out what number it is. And of course, 7 is greater than -7, so B is the answer here. So that was our first set. Get ready for the second one. Pull out that scrap paper again. And I think I'll give you the same amount of time here. Again, commit to an answer on paper for all three of these. Get in that habit of putting something down even when you're not 100% sure. Let's talk about these. Quantity A and the given information in the top problem, very similar. At least they both have Q's and P's in them, different numbers of them, but this is the commonality to exploit. Plus quantity B is just a regular number, so not much to do there. So one way to do that exploiting of the similarity is multiplying this by 2. At least that way you make a 4Q like you have in quantity A. But you have the wrong number of P's. Well, get the right number of P's by subtracting 2 P's from both sides of this inequality. So now what we've created is quantity A is greater than 18 minus 2P. We know that. That's the fact. Okay? Quantity A is greater than 18 minus 2P. But we want to know, is it greater than 18? Well, the answer to that depends on P. It depends on Q also, but a little more directly on P based on the work that we've done. Quantity A will be greater than 18 if P is 0, right? Because that's basically what this would say in that case. Quantity A would be greater than 18 if P were negative, great, because then this would be great. Quantity A would be greater than something larger than 18, and therefore definitely larger than 18. But if P is positive, for example, if P is 4, then this amount is 18 minus 8, or 10. And if quantity A is greater than 10, it might or might not be greater than 18. There's possibilities either way. And so what that means is D is our answer. It depends on both Q and P. And you could have plugged in Q's and P's from the outset, but when there's two variables at work and both of them have to sort of they have to follow this rule as given in this constraint, it's a little less free in terms of picking numbers. You're not free to plug just any old thing. You have to plug numbers that meet this constraint. So you might prefer algebra on that kind of problem. Let's turn our attention to the second question. P is a positive integer and a multiple of 5. Or sorry, x in this case. X is a positive even integer and a multiple of 5. So that's 3 constraints in one. It's positive, it's even, and it's a multiple of 5. Some of you may look at that and say, well, okay, I see that means x is a multiple of 10. You leap right to that, positive multiple of 10, in fact. If you're not quite there, tackle the constraints separately. So here's a little workspace listing the multiples of 5. Okay, that's that constraint. And then tackle the fact that it has to be an even integer. Just cross out all the odds. Those are disqualified by that second constraint. And then just look at what's left. These are all positive, so these are all still valid numbers. Okay, so if x is 10, 20, 30, 40, we now have to look at the remainder question. Now watch out. If you picked C on this answer, reasoning that all of these numbers end in a 0, and therefore A is equal to 0 just like B, you may be applying a shortcut, a rule that doesn't quite apply here. And that's the rule that when you divide numbers by 10, the remainder is always the units digit of the number that you're dividing by 10. Okay, so here the units digit is 0, so remainders would be 0. But watch out, we want to divide by 20. So actually do that. It becomes easy to see what's going on. If x is 20, 20 goes in one time and the remainder is 0. But if x is 30, 20 goes in one time and the remainder is 10. So A could be equal to B, but it could also be greater than B. That proves D. All right. Final question, probably the hardest in this grouping because there's some algebra going on and absolute values. Plus we have that squared term. So algebra approach is actually, I think, the best one. You can get there with number plugging, but I think the algebra will show you what numbers make sense to plug. And here's the algebra. Get all the variables on one side in that constraint. So just subtract x, y from both sides. Don't divide by x. It's tempting to do that since x is in both of those terms, but dividing by x is dangerous because you don't know what x is, and there's one thing you're never allowed to divide by, and that is 0. So what if x is 0? You'd be making an illegal move. So it's better to pull the x off to the side, just factor it out. And now we've got something times something equals 0. Think about number properties. 0 times anything is 0, right? So there's two solutions. Either x can be 0 or x minus y can be 0. And you'd end up with a product of 0. And those are our two solutions. So x could be 0, and that would mean y could be really anything. Or x could be equal to y, so x minus y is 0. And in fact, there's kind of an overlapping solution, which is x equals 0, which also equals y. And so there are cases where, if y is anything, y could be 100, and quantity b would be bigger than x equals 0. Or the two quantities could both be equal to 0, and they would be equal. And so it's not always the case that one quantity is bigger than the other. The answer is D. There's one remaining set in this segment, or in this lesson. Another set of 3. We'll put up the timer again. final set. So make sure you have 3 answers listed on your page. All right, we'll talk again top to bottom. For this first one, clean up quantity A as much as you can. So you may notice that 15 divided by 3 is 5. There's a similarity with quantity B. Maybe you'll be able to exploit that. There's also a rule about exponents. When you have a common base of 10 like this, and one exponent's divided by the other, the rule is that you subtract the exponents. So there's a commonality too, kind of in disguise. P minus Q is really part of both quantities. So quantity A looks like this. You can cancel zeros. 1,500 divided by 3 gives you 500. We've rewritten that 10 to the P over 10 to the Q in its alternate form. And so now what you've got is 500 times something versus 5 times that exact same thing. And 500 of something is bigger than 5 of something if you're dealing with positive numbers. So let's think about this 10 to some power. It turns out that 10 to any power is going to be positive. And that may seem counterintuitive, like 10 to the 0, how is that positive? Well, anything to the 0 is 1, and 1's a positive number. Yeah, but what about negatives? What if you do 10 to the minus 2? Well, negative exponents don't make for a negative result. They just mean 1 over the regular positive exponent. So 10 to the minus 2 is 1 over 10 squared, or 1 over 100. That's a small fraction, but it's still positive. So no matter what, if this exponent is negative, 0, or positive, no matter what, 10 to that exponent is going to be positive. And so what we're really looking at is indeed 500 times some positive versus 5 of the same positive. 500 is more, so A is the right answer. All right, so if you pick D there, maybe you got confused about the exponent thing, mistakenly thinking that maybe that could be negative sometime. Worth running through a couple numbers just to verify that rule. All right, for the second question, we've got that given constraint of x squared equals 4. And we've seen even exponents earlier today. They hide the sign of the base, so there's actually 2 solutions there. X could be 2 or negative 2. Okay, so we're not plugging randomly here. We're just going to plug in those only 2 allowable values. See what we get. And we've got an odd exponent in A, so we've seen that before. What happens? The sign is different in the result, 8 versus minus 8. And with quantity B, it's just a straight up addition. So be careful. Remember that we're not just comparing all 4 of these numbers willy-nilly. If X is 2, A is 8, and B is 8. Okay, that's the comparison to make between 8 and 8. The other possibility is that if X is negative 2, we're comparing minus 8 in A to 4 in B. Those are the only 2 comparisons, and you get 2 different results. Either 8 is equal to 8, or 4 is greater than minus 8. Answer there is D. We've proven it as we did before, but they gave us the 2 cases to try. The last one is the most interesting of the bunch. More words means more translation of what's going on. And we're given an average of 4 numbers, 4 variables. We know that the average is 50. The other thing that you should remember about averages is just how do you get them? You sum up A, B, C, and D, divide by 4, because that's how many terms there are, and then you get 50 as your average. So you could write this a different way, right? If sum divided by number of terms is the average, the sum actually equals the average times the number of terms. And here the sum is going to be more useful to us. You can glance down at B, quantity B, to see why. And so if 4 numbers average to 50, they sum to 200. If 3 numbers average to 10, they sum to 30. 3 times 10. And from that you can back out. If the sum of A plus B plus C is 30, D, the remaining number, must be the remainder. 200 minus 30, D is 170. And quantity B is kind of sophisticated. A, B, and C are all positive numbers. They sum to 30, so the sum of any two will sum to something less than 30. And A is definitely bigger. So that's the end of this segment. As you go off and do your own practice quant comparison questions, try doing them both ways. I think it's a good practice to try both plugging numbers and also try algebra wherever you can. If nothing else, you'll become a more flexible test taker and decide for yourself where you like to use each approach. Good luck.